Hello there, algebras, and welcome to your Chapter 13, Lesson 3 notes, a little bit of mixed review of arithmetic and geometric. So starting right off with what is the difference between arithmetic sequences and geometric sequences? Well, arithmetic sequences have a common difference and are linear in nature because that common difference is a constant rate of change. Whereas geometric sequences have a common ratio or R value and are exponential in nature because we're dividing our second term by our first term to get that commonality of our base in what we're raising to our different powers. So when I look at two different sequences, I can identify what type of sequence I have in the same fashion that I determine the D or R value. So what I would start with is I would take the second value and I would start by dividing it by the first value just to see what I get. And then take that value and subtract and see what I get. So my common ratio might be 2, my common difference might be 20. Now let's test that with the third minus the second, the third divided by the second. So third divided by the second gives me that same common ratio. And when I subtract, notice I do not have a common difference. So that tells me two things. That tells me that this is a geometric sequence and that I have an R value of 2. Now you will notice between the two functions, or excuse me, the two sequences that I'm looking at right now, the A value is of course 20, the same for both. And even the second value is the same for both. Notice it deviates later on depending on what we're using. And then each of them has an 80 as one of its terms in its sequence, but which term is it? In the case of my current sequence, 80 is the third term in my sequence. So a to the subscript 3 is 80 here. All right. And now what we're going to do is name the particular function that this is being modeled. It would be exponential. We're going to do that for the second function as well, or excuse me, second sequence as well. So again, notice I was able to determine a common ratio. I've already used 20 and 40. So now what I'm going to keep doing is using the third term and the second term. So 60 minus 40, look at that, gives me that common ratio of 20. So this time I know I have an arithmetic sequence. Because I was given a D value of 20, they actually are subtracting to give me the same value as I go. So my initial value still is 20. So both my D value and my initial value are the same in this case. That's not always the case. Then here I am looking at, what's 80? This time 80 is my fourth term in the sequence. So that would be A to the subscript 4. And what is the function being used? That'd be a linear function. Okay. For each of these, so for each of these, I'll just use A to the subscript 8 for both of these so that we can turn them into our into each of the formulas and then find the 8th term in each sequence. They both are infinite, so we are able to continue going on in each of these sequences. So let's start with this one. We know our A value, we know our D value, and now we know we want an N value of 8 when we plug in. So we'll say A to the subscript 8 is equal to 20 plus 20 times 8 minus 1. and I can just plug that straight into my graphing calculator. Even though the numbers aren't that difficult, you could probably do them in your head. It's still kind of wise to be plugging into your graphing calculator and know how to do that. So the eighth term in this sequence is 160. We already know that that's the fourth term in our geometric sequence over here, that starts out kind of similar. So that's clearly not going to be 160. Here, again, we want to find our n value of 8. So a to the subscript 8 is equal to 20 as our initial value, times 2 is our common ratio, raised to the 8 minus 1 power. So make sure you know the difference as to how to type these into your graphing calculator. And this time, our eighth term is 2,560. Okay. So what we'll do here is I'll have you experiment a little bit with number 3. For both A and B, we want to find the 10th term in the sequence. But in order to do so, you need to know, is this arithmetic or geometric? Okay. I'll let you figure that out and then give me common ratios or common differences and the 10th term in each of those sequences. So pause it right here and give those a try. All right, let's check our answers. Let's make sure that we had geometric for A, and our R value was 0.5. So again, I found that from dividing 72 by 144, 36 by 72, and I was realizing that division was giving me the same R value all the way down. So that is the common ratio. That is a geometric sequence. My A value, 144. My N is 10. Plug them in, plug into the graphing calculator. This was not one where I had kind of been indicated to do a fraction or a decimal, so I kept it in decimal form. Over to B, it's arithmetic. Your D value is 9. And I think that you're starting to be able to tell when something is going to be a geometric pattern or an arithmetic pattern. You can usually quickly see the terms increasing or decreasing at a rapid rate for geometric, aka an exponential, right? Versus a constant rate of change is a little bit easier to pick up on. Okay, so a constant rate of change. There's 9, there's 9, there's 9, there's 9, right? It's not increasing super rapidly. All right, so let's keep going with our mixed review. We will skip D and C for the time being and instead head down to just looking at the types of functions that we have here that kind of get automatically figured out by our values giving us the patterns of exponential or linear. So again, how you're looking at each of your different functions is if you're given a sequence, the first term in that sequence goes with 1. That's your n value. So you're not going to have an n value of 0. Then you put that number in as the a sub n. So 2 would be my negative 5.5. 3 would be my negative 3. The fourth term would be negative 0.5. Okay. And I can also see already that this is a linear pattern. It's an arithmetic. And a linear pattern comes with that. So let's prove that by getting our common ratio. So negative 5.5 minus negative 8. Oops. Negative 5.5 minus negative 8 gives me 2.5. Negative 3 minus negative 5.5 gives me 2.5. So there's my D value. And that essentially is my slope. So now if I'm graphing down here, we've got 1 all the way down to negative 8. We've got 2 down to negative 5.5, 3 down to -3, and 4 down to -0.5. We do not connect because this is discrete. So this is linear and it is discrete because there are not, there we go, there are not any terms in between each of these term numbers, 1, 2, 3, 4, etc. So now take a peek at the other one, and you can actually see that this is exponential in nature. So term 1, 2, 3, and 4, those are your x values. You can see n sub 1, that's -8. So we have the same a value again. Then we've got -4, -2, and -1. This is geometric, also exponential. And this time there's an r value, and let's figure out what that is. So we take -4 and divide it by -8 to get 0.5. And -4 divided by -2 divided by -4 is the order we need to go in. The third term divided by the second term. And -1 divided by -2 gives us the 0.5 that we've been continuing to get, or 1/2 if you prefer 1/2 as the fraction. Now let's graph that. So +1 down to -8, same start. But now you'll see 2 down to -4, 3 down to -2, and 4 down to -1. So you really can see the curving nature versus the linear nature. And that would be the exponential. And again, this is discrete because there are not going to be any more terms in between the terms we have. There are no terms between -8 and -4. So if I connected right here, I'm implying that there are terms in between those, and there are not, so we do not connect. Alrighty. Last but certainly not least, how has the Regents asked these questions? Always the question that we're kind of thinking to ourselves. So we've got a Petri dish contains 4 viruses. Each hour, the number of viruses increases as shown in the table. The population change can be modeled by a geometric sequence. So we're actually told that right now, that we need a geometric sequence. We want to write a formula that models this and use the formula to predict the nth hour, the 7th hour. Okay, so let's give this a shot. Our A value is 4. There we go. Let's see. We know it's geometric, so we know we need an R value. So let's figure out what that is. So 12 divided by 4 is 3. 36 divided by 12 is 3. 108 divided by 36 is 3. So it looks like our R value is 3. So let's plug this in. A to the subscript 7 is equal to 4 times 3 raised to the 7 minus 1 power. So let's figure out A to the subscript 7. 4 times 3 raised to the 7 minus 1 power. Oof. Exponential growth. There we go. Let's actually just double check ourselves since this is a Regents question. So here's the formula. That's A. Here is the answer. That's B. And I'm just going to double check myself. So if I was left off on the fifth hour gave me 324 in my population, then let's do the 6th hour right here and the 7th hour right here just to make sure. So I'll take 324 and I'll multiply by 3. Okay. And I'll take 972 and I'll multiply by 3. Oh, good. So that's my double check that I did get the same answer, but this did specifically ask me to write the formula, so to model the sequence. So I had to use that to give me my final answer. All right. Let's look at this diagram below. We've got term 1, term 2, term 3. Assuming the pattern continues, which formula determines A sub n, the number of shaded squares in the nth term? Oh, shaded squares. Okay, so let's take a peek. Let's count our shaded squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I added 4. I added 4. If that pattern continues, now this is a challenging question. Just look at how they have it. If that pattern continues, I know what my A is, it's 12. I know what my D is, it's 4. And if I plug that in and keep the N, watch this. This is why you want to make sure that you're paying attention here. If I plug this in, A to the subscript N, so this is the general pattern, means I started with 12. I'm adding 4 times N minus 1. I kept the N, right? What that does for me is means I have to distribute this to go backwards and find. Remember, this is A sub 1. The y-intercept would be an A sub 0. So if I want that form, I need to distribute this and simplify. So I get 12 plus 4n minus 4. What's 12 minus 4? It's 8. Should be positive 8. So be very careful about that. A former regents question where we weren't just leaving it right here. We had to actually distribute and simplify. All right. Let's work on that homework where we have some mixed review, and then we will get into recursive sequences next we meet. Thanks, guys. Have a great night.